Hi everyone, I'm Yujia from Stanford University. Today it is my great honor to present here the complexity of infinite horizon general sum stochastic games. The talk is based on joint work with Vidya Muthukumar and Sidford. Let's first look at a basic mathematical model Markov chain. It is composed of three parts: states, transition probabilities, and rewards. At every state, there is a transition probability vector to the other states which characterize the transition. This could be either randomized or deterministic. While we do not have any decisions for players to make here, we can still have different players for a Markov chain. In the model, we can define instant rewards that each player will receive at each state, which we denote by R. This may be completely independent among players. In general, this can be defined for arbitrary many players too. The utility of a player is defined by collecting all the instant rewards she receives throughout the process. There are two well-known notions of utilities: the average reward and discounted reward. They are well defined as long as we fix some initial distribution over the states. Given an initial distribution, the notion of average reward computes the long-term average of instant rewards that the player receives throughout the process. As an example, we show here how to compute the average reward for the first player. On the other hand, the discount reward computes the infinite sum of discounted rewards, where we discount more for steps further in the future. Here we give an example to compute the discounted reward utility for the first player. Now we have gone over the basics of Markov chain. How is that related to our topic today? Actually, the most general game model I'm going to talk about is simultaneous stochastic games. It is basically a generalization of Markov chain for multiplayers by incorporating the decision-making process into it. Besides the three basic components for Markov chain, it also has actions defined for players. Consider again our toy example with two players. We now give these two players control on the two states. This means that they respectively have some action they can choose to take from at each state, and their joint actions decide the transition probability vector and also their instant rewards. We call the strategy as the collection of all players' actions for each state. Note that we not only allow deterministic or pure strategies, but also allow randomized or mixed strategy for each player. For a fixed strategy, the model still reduces to a Markov chain, and the utility of players could be measured similarly as we mentioned. The goal for studying simultaneous stochastic games is to find strategy that achieves Nash equilibrium of utilities, or do so in an approximate sense. These types of games are very prominent in our daily life. For instance, in autonomous driving, the future state depends on both other drivers and your own action, and different drivers may have completely different goals. Thus, this becomes a natural instance of simultaneous stochastic games. While the games we introduced previously are very general and very natural, there are also two important special cases which are interesting on their own. One class is known as turn-based stochastic games. Basically, it has the same components. The main difference is now for each state, we assign a controller, and only the controller can pick different actions at that state. Here in our toy example, green player controls the green state, and gray player controls the gray state. Only the controller's action will decide the transition probability and the reward that each player receives at the state. Here, the strategy corresponds to the collection of controller's action for each single state, which of course can still be randomized in a mixed strategy. When fixing a strategy, this still reduces to a Markov chain, and the utility can be measured in a similar way. The goal for studying turn-based stochastic games is also to find a strategy that achieves the Nash equilibrium or do so in an approximate sense. These types of games are very popular. For instance, in a chess game or a board game, the game iterates round by round among the players, and at each round, only one player takes the action. Those are natural examples of turn-based stochastic games. Putting all these classes together, we start from Markov chain, which characterize transitions on the states. When we want to further incorporate decision-making of more agents in the games, here comes turn-based stochastic games and simultaneous stochastic games. We make a few assumptions on the model we study. First, we assume state and action spaces are finite. Next, we focus on learning stationary policy, which does not depend on the time step t. Third, we assume all instant rewards received are non-negative for all players. Finally, we focus on well-conditioned class of games, meaning that the model parameter 1 over 1 minus gamma for the discounted games and t-mix, the mixing time for the average reward games, are both polynomially bounded by the problem representation size, for example, the state size and the action space size. There are a few facts that people already know about these problems. For simultaneous games, people do believe that it is a hard problem. More concretely, they are known to be at least p-pad hard, since the simultaneous stochastic games with a single state will reduce to a normal form games, which is known to be p-pad hard. Here, I'm not going to talk about the formal definition of p-pad complexity class, but basically, you can think of it as equivalent to solving an approximate Nash equilibrium of the two-player general sum games. For turn-based stochastic games, people don't have any idea about how hard this problem is. There indeed are some facts hinting that the problem may be easy. For instance, we do know that zero-sum turn-based games is easy. Single-state turn-based games, as opposed to the simultaneous counterparts, degenerate to a single-state Markov decision process and consequently are also easy. And computing non-stationary Nash equilibrium for turn-based stochastic games are also known to be easy. So, based on these known facts, our work gives a more complete picture of the complexity of this class of games. In particular, we show that SSG is not harder by two-player general sum normal form games by formally establishing the membership of finding an approximate Nash equilibrium of SSGs inside the p-pad complexity class. For turn-based stochastic games, we show they are just as hard as SSG, although being more structured. We prove the p-pad hardness of finding an approximate Nash for turn-based stochastic games. We also managed to identify an easy subclass of turn-based games which have a nice local reward structure. We prove for such special class of turn-based games with localized rewards, we can indeed design polynomial time algorithms using the potential game idea. First of all, before diving into our techniques and how we achieve all these results, I'd like to give a little detour on the common challenge for studying these classes of games. The common challenge is the utility function for player I, which we denote by ui, as a function of strategy of player I pi I and other player's strategy pi minus I. This utility function is not necessarily linear, convex, or concave in the variables. To illustrate this point, here is the visualization of the utility function for some fixed single-player MDP with 5 states. When fixing actions on all the other states and only changing strategy on state 1 linearly, the blue figure shows how the utility will change, and it turns out to be a nonlinear and non-concave function. When fixing actions on other states and changing strategy on state 2 linearly, the red figure is nonlinear and non-convex. This suggests that applying the classical optimization toolkit to these problems might be tricky, and try to construct hard instance by playing with the utility function also seems to be tricky. So to overcome these challenges, our core idea in the study is try to linearize all these games. The key observation we make is that games with linear utilities are relatively much better understood. For instance, for two-player general-sum standard games, which we use to define the p-pad complexity class, they are a classical types of games we mentioned earlier that by definition has linear utilities. For each player I, their utility is characterized by a matrix AI. When they each play strategy pi1 and pi2, the utility is simply pi1 transpose AI pi2. Actually, due to this nice linear property, they are the first ones that people are able to establish p-pad complexity results for. For turn-based games and stochastic simultaneous games, we try to view them as a generalization of general-sum normal form games. In fact, although the utility functions they have are nonlinear, we show they satisfy a pseudolinear property. To formally explain what this property is, let's fix a player index I and a state S. Fix all the other player strategy pi minus IS, and consider two different strategies player I play at the corresponding state S, which we call pi IS and pi prime IS. We could define a strategy function pi theta, which linearly interpolates the strategy induced by pi and the strategy induced by pi prime. Note when theta changes from 0 to 1, only the strategy of player I at state S will change, and all the other policies will remain unchanged. The pseudolinear property essentially says that the slope of the utility function of player I between any points pi theta and pi 0 is close to the slope defined by pi 1 and pi 0 by a multiplicative factor of rho. As an illustration, suppose we have the utility at pi 0 and pi 1 as in the figure. We could connect them by a linear function, and we show ui pi theta will not have slope too different compared with the slope of this linear function for any theta between 0 and 1. This pseudolinear property actually has several nice implications. First, when the multiplicative factor rho equals to 1, this property basically implies the utility is a linear function in player I strategy pi I. So in general, it could be viewed as a generalization of the linearity. Second, this is actually a stronger condition than the element-wise monotonicity. This condition implies a coordinate-wise monotonicity of the utility function, which actually suffices to ensure the existence of mixed Nash equilibrium for those kinds of games. So this property also gives an alternative way to prove the existence of Nash equilibrium. Also, under mild extra conditions, this pseudolinearity suffices to show that the problem is not harder than general-sum normal form games, which lie in the p-pad complexity class. Finally, together with other structure of turn-based games, this helps us to show that solving turn-based games are also as hard as general-sum normal form games. This helps us to establish the p-pad hardness result. However, this hardness result is not an immediate consequence of just the pseudolinear utilities. To prove that, we also need to design game gadget to implement arithmetic circuit gates. Due to the time constraints, I'm not going into the detail of these constructions, which may be a little bit complicated. Basically, here are how we implement all the different arithmetic gates by carefully designing instances of turn-based games and choosing the right instant reward and transition probability vectors. I'm very happy to talk more about them during the in-person meeting. On a high level, the pseudolinear property gives us a way to view turn-based games and simultaneous games as not being too different from general-sum normal form games. And consequently, they establish their complexity similarly as people do for general-sum normal form games. It is worth mentioning that a concurrent independent work by Costas, Noah, and Kai-Ching further established the hardness result for two-player turn-based games. Another interesting part in our paper is a positive result on efficiently solving structured turn-based games with localized rewards. The way we achieve this result is by viewing these types of games as variants of potential games. In game theory, people have defined potential games, or Markov potential games, where there exists a potential function phi such that the difference of the potential function's value could basically capture all the differences in each player's utility, assuming that player has changed her strategy. On the high level, we try to relate turn-based games with this extra localized reward structure to Markov potential games. The special case of turn-based games we study are local reward instances. Basically, we assume each player could only control at most one state and only receive a non-negative instant reward at the state that she controls. For all the other states she doesn't have control, she will only receive a zero instant reward. We call this kind of instance as local reward turn-based games. Under such assumptions of localized reward, by algebra, we can write the utility function as this nice form. For each player I, the utility is the product of a function fi that only depends on player i's strategy times a function gi that only depends on other players' strategy divided by a general function h. H depends on all players' strategy but are the same for all players and doesn't depend on I. Under such structural property, we can show the utility ratio between the two policies can be essentially bounded by the ratio of some defined potential function phi for the phi properly defined here. Because of this nice ratio equivalence property, this essentially established the potential condition we need for Markov potential games in the logarithmic space. This log space potential game condition allows us to show several nice properties for such games. First, we can show there must exist pure strategy Nash, where no player needs to play a mixed strategy. Second, this allows us to design polynomial time algorithm for the problem. The polynomial time algorithm we consider is a type of method that basically just alternates between the coordinates and prove it converges in polynomial time. By showing at every suboptimal point, we are able to make big enough progress in terms of the potential function. This helps us to show that the alternating coordinate-wise algorithm indeed is a polynomial time algorithm, and this class of localized reward turn-based games indeed is a class of games that can be efficiently solved. So putting all the things together and in conclusion, we show the complexity picture for multiplayer games about finding an approximate Nash equilibrium in either the simultaneous stochastic games or the turn-based stochastic games. We show finding approximate Nash in both these kinds of general games are p-pad complete. We also design new efficient polynomial time algorithms for solving structured turn-based games. These kinds of results all come from relating these games to other classes of well-studied games. For instance, for simultaneous and turn-based stochastic games in general, we reduce them to show the equivalence with two-player general-sum normal form games, which has a linear utility structure. For turn-based stochastic games with localized reward, we relate them to the Markov potential games and show that they satisfy this potential game condition in the logarithmic space. We hope these ideas of relating different classes of games could find further utility for studying broader classes of multiplayer games too. This is the end of my talk. Thank you very much. I'd be happy to take any questions and discuss more about the details of our work during the in-person conference. Thank you.